So what we're going to do now is we're going to look a little more in depth at the different prompts you could receive on the AP test and deciding whether or not to use the intermediate value theorem, the extreme value theorem, or the mean value theorem when answering it. First, we're going to review intermediate value theorem and just kind of decide whether or not our IVT applies in the prompt that's given. And so we'll go through, we'll read the criteria that's being presented and then decide whether or not your IVT applies or does not apply. And then if you want to write your explanation there, that's fine. I'm just going to kind of talk through the process. So let's look at the first one. The following table gives some function values for the continuous function g of x. Therefore, there exists some r in the interval 0 to 2 for which I think this is supposed to say g of r equals 5. So the first thing that has to be true about a function if you're going to use the intermediate value theorem is that it has to be continuous. So we can kind of check mark that as something that we notice already or see that that criteria is being met. Then we're trying to show that there is a value r between 0 and 2 that when you plug it in you get 5. So what I need to find out is what g of 0 and g of 2 equal, because if they equal numbers that surround 5, then we know that to get from, -4 to 18, you would need to hit 5 in the middle. So there would have to be a value r that would make that true. So let's find g of 0 first from the table, which is 7, and then g of 2, which is 3. And so we can say, yes, the IVT does apply because we have a continuous function. And when you find the y-coordinates of the interval you're considering, you get values that are around 5. Therefore, there must be some r in this interval between 0 and 2 that would also produce 5 as an answer. So, yes, your IVT applies. All right, so in the next portion, we have let k be the function defined by this. There must exist some x between 0 and 2 for which k of x equals 4. So the first thing I notice is that they don't tell me the function is continuous, but that's something I can check on my own as well. So for piecewise functions, we would know that a function is continuous if your function is defined. So we would look for k of 1 being defined because that's the breaking point. So k of 1 would be 3. That's also my left-hand limit of my function. And then I just have to check and see my right-hand limit as well. Oops. My right-hand limit is 5. And so since my function is not continuous, or I guess you can just put a little c with an x next to it, because my left-hand limit and my right-hand limits don't match, I can't apply the IVT here. One thing to note is if this had been a different interval, so if this interval had been between, like, let's say 5 and 7, we wouldn't have even had to have checked for continuity at 1 because 1 wouldn't be in the interval. So if we were looking at between 5 and 7, we would have really only been considering this bottom part of the function down here, and this is a linear function that would be continuous. So it's not necessarily just is your function continuous in general, but is it continuous on the given interval? Now for this problem, it wasn't, so we would go ahead and say we can't apply the IVT here. So because it's not continuous from 0 to 2, 1 is causing problems. For this function, consider the function s of x equals 2x squared plus 4x. There must be some a between 0 and 1 for which s of a equals 3. So I know this is a continuous function because it's a polynomial, and all polynomial functions are continuous for all real numbers. And then we just really have to see if s of 0 and s of 1 surround 3, because then you could apply your intermediate value theorem. So s of 0, in this scenario, we actually plug in the x value, so we get 0. S of 1 would equal 6. So, yep, check, your IVT does apply because we have two y coordinates that when you plug in the interval to your function, your y coordinates surround the given y-coordinate, and so there has to be some a value that when you plug it into s, you get out 3, because you can't get from 0 to 6 without hitting 3. All right, let's go ahead and look at 4. So for this function, we're looking for v of x equaling 1 for some x value in the interval 0 to 4. So let's go ahead and check that continuity first. So this is a piecewise function, so I'm going to check the breaking point and find v of 2, which would be 1 minus 2 would be negative 1. That's also my right-hand limit. Okay, then I'm going to go ahead and check the left-hand limit. And when I plug in 2 there, I end up with 2 times 2 is 4 minus 1, which is 3. So this function is also not continuous on the interval because the interval that we're considering is from 0 to 4, and 2 is in that interval, so we can't use IVT. All right, which of the following statements follows from the statement, if f is continuous on the interval 1 to 4, with f of 1 equal 3 and f of 4 equal 9, then there exists at least one value of c in that interval for which f of c equals 7. Well, that makes sense, right? Continuous function, f of 1 and f of 4, 3 and 9 surround 7, so there has to be some c value between 1 and 4 that when I plug it into my function, I get out 7. Okay, so now let's check these statements. So if f is not continuous on 1 to 4, with f of 1 equal 3, f of 4 equals 9, then there is no value of c in the interval 1 to 4 for which f of c equals 7. Well, that's not necessarily true, but let's go look at the next statement and we'll see. If f is defined on the interval 1 to 4 with f of 1 equals 3 and f of 4 equals 7, and if there is no value of c in the interval 1 to 4 for which f of c equals 7, then f is not continuous. So I think in this scenario, it's best to go with B, and I want to talk about why. So this one has to be true because if you have a function that's defined on 1 to 4, so that means every single point, there's a point on every number from 1 to 4, and you know that f of 1 equals 3, so if I was going to graph it, it would look like this. F of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then 1, 2, 3, 4. Okay, so there's 1, there's 4. F of 1 is 3. 1, 2, 3. F of 4 is 9. Here. And I know my function is defined along the whole path. So I have a whole path of my function, which means every point has a point somewhere. So they have to be connected. But what it's saying is that there is no value of c in the interval for which f of c equals 7. So it means that no matter what I do, I can't, whoops, that's a little high, isn't it? There you go. No matter what I do, I'm not allowed to hit this value. So the only way that I could do this and have a function that's fully defined from 1 to 4 would be if I had a discontinuity and did something like this. So that's why this statement is 100% true. Your function might not be continuous on 1 to 4, but that doesn't mean that you definitely don't equal 7. It just we can't confirm it, right? We could have this scenario, but it could we could equal 7. So for example, if I have a function that's not continuous, here's 1, here's 4, oops, there's 3, there's 9, right? So like I could have a point here, and then I could have a point up at here, 4, 9, and then all of my points in between could be at 7, right? That would be an opportunity. So f is not a continuous on 1 to 4, f of 1 equals 3, f of 4 equals 7. They're saying no matter, as long as this stuff is true, there can't be a value of c for which f of c equals 7. But we just showed that that's a possibility, right? I have the points, and I have my functions not being continuous, but I definitely can hit 7 in a bunch of different ways. So this statement might be true, but it doesn't necessarily have to be true, which is what separates it from B. B 100% has to be true. All right, let's go on to IVT or EVT. So now we're going to kind of differentiate between these two guys. So the extreme value theorem states that if your function is continuous on the interval, then f of x is both an absolute maximum and an absolute minimum on that interval. So a table is shown with selected values for the twice differentiable function below, and we're going to decide whether these statements, whether the IVT or EVT applies, okay? So since our function is differentiable, it's also continuous, right? You can't reach differentiability without getting through continuity. It follows the alphabet, right? I can't get to the letter D in the alphabet without hitting the letter C on the way. Since k of 6 equals 2, k of 6 equals 2, and k of 7 equals 0, and since 1 is between 2 and 0, so they're saying that 1 falls somewhere in here, it follows by the blank that k of c would equal 1 for some c between 6 and 7. Well, that's just showing a value is in between two other values, so that's your intermediate value theorem. Okay, now let's go ahead and talk about the next one. There must be a minimum value for k at some r in 1 to 7 because k is differentiable and therefore also continuous. So anything having to do with a minimum or a maximum value right off the bat, or like proving that it is there, that's your extreme value theorem. It doesn't say that it's between two things. It says that there is a very lowest point on the interval 1 to 7. Okay, now let's look at this one. There must be some value a in 2 to 6 for which f prime of a equals 0 because k is continuous and therefore k has an absolute maximum on 0 to 6 by the EVT because you are talking about an absolute maximum, not necessarily that a number falls between two things, but you're talking about that there's a maximum value. All right, so now since k is twice differentiable, then k prime is differentiable and therefore also continuous. It follows by the blank applied to k prime that k prime of c equals some c k prime of c equals 0 for some c in the interval and therefore in 4 to 6. Now this doesn't say anything about a max or a min, and even though we don't have enough information to decide anything about k prime and whether or not this is actually true, basically what it's coming down to is that this isn't saying that this is some minimum or maximum value, so it's talking about a value that's going to fit between two other values, so we would say IVT for this one. Okay. All right, in number 5, we are given, it says, which of the following statements follows from this statement? So if f is continuous on the interval a to b, then f has an absolute maximum and minimum on a to b. So that is the extreme value theorem. And now we're just going to check and see whether these statements follow directly from here, okay? If f has an absolute maximum and an absolute minimum on a to b, then f is continuous on a to b. Well, that's not necessarily true because I could have a graph where I have a point up here and then it does this and then it breaks and then it comes down here and then it hops up and then it extends here. So this definitely has a maximum, a very highest maximum and a very highest minimum, even though it's a discontinuity. So that's not necessarily true. If f has an absolute maximum and no absolute minimum, then f is not continuous on a to b. So let's see. So here's a to b. So it has an absolute max, so we'll make that the highest point, but it has no absolute minimum. Then f is not continuous on a to b. Well, that looks continuous, but I don't know if I can include hard brackets on that. We'll come back to that one. Every function with an absolute maximum also has an absolute minimum on a to b. Oh, not necessarily. Like you could have a function that is here's a, here's b, and our maximum could definitely be in that interval. So I could have like a point that starts here, it could go really high, there's the maximum, but your minimum could be like afterwards. It doesn't have to happen on a to b. So that one's not necessarily true. And then if f is not continuous on a to b, then f has no absolute maximum and no absolute minimum. Well, we already kind of showed that in the first example for the graph, right? I said here's a, here's b. I have a not continuous function. So I have a function that does like this, and it comes down, and then it hops down here, and then it comes up, and then it hops right here, right? If f is not continuous, then it has no absolute maximum. This absolutely has a max and a min. Max, min. All right, so then going back to b, if f has an absolute maximum but no absolute minimum, then it's not continuous on a to b. I can't draw a completely continuous function, including the endpoints, that doesn't have a minimum without not including the endpoints, right? Like, so I could do a to b, whoops. I could do a to b with both having open endpoints, but then they wouldn't be continuous with the inclusion, right? Remember the hard brackets mean including that endpoint. And so there's no way I can draw a continuous function that has both endpoints that doesn't also have a minimum. So this would be the statement that kind of falls from it. It's almost like a converse or an inverse statement of this conditional statement. Awesome.